Jupiter? Because a graduate student came into my office and said, if you heard, a comet's going to hit Jupiter. And I said, Jupiter's really big. Comets are really small. It's not going to be a big deal.
And this was the question. What kind of an impact would a big snowball hitting a gaseous giant of a planet make? Gene Shoemaker believed that the incredible speed of the Shoemaker-Levy object would create a spectacular collision with Jupiter. But again, few believed him.
We didn't know that much about the makeup of comets, how strong they were. We just hoped for a big show.
Nobody thought that the results were going to be as dramatic as they were.
Shoemaker was right. The world watched from July 16th through the 22nd, 1994, as one after another, the fragments of comet Shoemaker-Levy 9 made a spectacular collision into Jupiter's clouds.
And these pieces kind of came in a line like a train, like a freight train, and just hit the planet, you know, bam, 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 bam.
Plumes rose 2,000 miles above Jupiter's cloud tops.
The fact that you could have fit the Earth within the dark cloud coming from one fragment strike, that was pretty awesome.
Awesome might just be an understatement. A 2-mile-long fragment in particular, labeled Fragment G, struck with an energy of 6 quadrillion tons of TNT, 600 times the power of the world's entire nuclear and conventional arsenal.
This is something that really happens once in a lifetime. Our understanding of the solar system is evolving by leaps and by bounds as we watch. That's the way to do science.
It proved beyond any doubt that impacts were not only possible, but inevitable and very dangerous. Some speculate that if a piece of a comet the size of Fragment G struck Earth, it could extinguish most life on the planet. An awareness of the continued danger of collisions in our solar system is just a part of Gene Shoemaker's legacy. In 1997, he died in a car accident while studying impact craters in Alice Springs, Australia.
I remember I was at a dinner where somebody asked someone that I know well, who is the greatest planetary scientist, who is the greatest geologist of the 20th century, and he didn't even think. He said Gene Shoemaker, without a doubt.
Gene Shoemaker helped the world understand that impacts within our solar system are still disasters waiting to happen. But have massive impacts also helped form our planetary neighbors, change their makeup, and even their posture? A chunk of solar system debris, 1/10 the size of Earth's moon, hurtles through space. Rocks and debris cross its path and get obliterated, leaving pockmarks on its surface. It's on a collision course with Mars. The impactor and Mars are about to test the ability of two objects to occupy the same space at the same time. The planetoid slams into Mars in a cataclysmic collision, scattering dust and debris. It's just another rough day in the life of the inner solar system 4 billion years ago. This was the largest impact our solar system has ever endured, yet the evidence was all but hidden until just recently. The mystery began in June of 1976, when the Viking 1 orbiter cruised through space at the tail end of a 10-month journey to Mars. As it began its orbit around the red planet, it started sending images back to Earth. The orbiter and its companion, Viking 2, completed more than 2,100 trips around the planet and sent back photos of Mars canyons, craters, volcanoes, and lava plains. The photos also revealed a curious division in the planet's surface.
Mars has what we call a hemispheric dichotomy, where the northern half of the planet is sitting at a low elevation and has a very smooth surface, but the southern half of the planet has a high elevation and has a much rougher surface. And we've known about this dichotomy actually for about 30 years now. The big mystery has always been how it formed.
In the 1980s, astronomer Stephen Squires and geologist Don Wilhelms proposed a radical theory to explain the dichotomy in the Martian surface. The so-called giant impact theory rests on the idea that the northern lowlands of Mars may actually be the largest impact crater in the solar system, as big as Asia, Europe, and Australia combined, covering roughly 40% of the Martian planet. But there were problems with this theory. Scientists studying the outline of the crater saw what appeared to be more of a kidney bean shape, and not the ellipse that would have been expected from this type of impact. Recently, a team of scientists, including Jeffrey Andrews Hanna and Bruce Bannert, set out to create a clearer picture of the impact crater. Using topographical and gravity measurements, they were able to look below lava flows in Mars' Tharsis region, which contains some of the largest volcanoes in the solar system. Once they subtracted the effects of volcanic activity, they could see the crater's actual shape.
So we were able to look at what was there perhaps 4 billion years ago. And when we did this, we found that the boundary, instead of being this very irregular kind of kidney bean-shaped thing, turned out to be this very regular ellipse.
This was a very important observation because there's really only one process that we know of that's capable of producing an enormous elliptical depression like this, and that's a giant impact. The largest impact basins in the solar system are all actually elliptical in shape.
Simulations indicate that the impactor would have to have been around 1,200 miles in diameter, or roughly the size of Pluto, hurtling through space at 20,000 miles per hour and striking Mars at a 45-degree angle.
So it's an enormously energetic impact.
Not surprisingly, the Mars impact is estimated to have occurred during the late stages of our solar system's formation, 4 billion years ago. And it is one of two massive planetary impacts that still scar our solar system. Evidence of the other impact can be seen in the off-kilter attitude of Uranus. As solar system planets go, Uranus is fairly dull. It has rings, but they are not nearly as spectacular as Saturn's. An ice giant, Uranus is puny compared to its gas giant neighbors, Jupiter and Saturn. Like Earth, Uranus has a solid core, but this is where its similarity to Earth ends.
We couldn't land a spaceship on it. It's got a thick, thick atmosphere, so heavy that it was almost like a pudding.
And that pudding sits on a bed of ice that makes up the ice giant's mantle. But the one spectacular feature that sets Uranus apart from the other planets, Uranus is extremely askew. For years, this strange alignment of Uranus baffled astronomers. But one leading theory first suggested by Soviet astronomer Viktor Safronov in the 1960s suggested that the cause was a massive impact from an object perhaps as big as Earth.
All planets have a rotation axis, so here's the planet, here's the North Pole, South Pole, and we're leaning at 23.5 degrees, Mars is leaning at 25 degrees, Jupiter's about 0 degrees. But Uranus is very strange because it's actually tipped a little bit past 90 degrees. And Safronov pointed out that you could do that by hitting Uranus with something that, as I remember, was 3% the mass of Uranus itself. So imagine a planet rotating like this. It's a round planet. It gets maybe hit tangentially right at the top, and that tips it over, you know, the debris gets thrown off, and you've now rotated this planet off to the side.
Not only do impacts knock planets on their side, like Uranus, and give the surface of planets complete makeovers, like what happened to Mars, but objects can hit planets so hard, pieces break off, only to fall into other planets. We know meteorites can land in fields, deserts, and just about anywhere else. But every so often, these meteorites are actually dislodged chunks of other planets, bringing us information from another world. Our solar system isn't a tidy place. Chunks of debris that never coalesced into planets float around in the asteroid belt between Mars and Jupiter, like so much unfinished business spoiling for a fight. Collisions beget collisions as impacts dislodge chunks of planets that themselves eventually crash into planets. These pieces are tangible evidence of impacts within our own solar system, impacts that happened billions of years ago, millions of miles away. And this chain reaction occasionally ends with these visitors from a distant place landing on Earth, bringing us information about the solar system.
It'll fly through the atmosphere at a tremendous speed and generate heat, pressure, start to burn, and Many times these fragments will explode in the atmosphere and then rain down on the planet in showers.
Every child who has looked at the sky and seen a shooting star has seen an impact of extraterrestrial origin. Many of us have seen cosmic collisions. We just didn't realize that's what they were.
Meteors burning up in our atmosphere are common, but infrequently, some part of the meteor will survive to impact the Earth. By virtue of its survival, it has earned the right to a new name, meteorite, and it now has a bounty on its head. A rare breed of people, meteorite hunters, make it their business to track down these precious rocks that have traveled through our solar system in a pursuit that is part science, part commerce, and part hobby turned obsession. Jeff Notkin and Steve Arnold are two of the world's most prolific and determined meteorite hunters.
Sometimes we travel to godforsaken corners of the world that nobody would want to go to in their right mind, all in the hope of finding little pieces of cosmic debris. Why do we do it? Meteorites are amazing. They're a chance to hold a bit of an alien world in your hand.
They're also treasure, these pieces of other planets that land on Earth. There's a hierarchy of meteorite value. Not surprisingly, the rarest rocks have the most value.
Pieces of the planet Mars were blasted off into space by other meteorite impacts on the surface of Mars. Of the many, many thousands of different meteorites that have been found on our planet, only about 30 are from Mars. So they're among the rarest extraterrestrial material that we've ever recovered.
Martian meteorites are 35 times more valuable than gold by weight. But most meteorites are refugees from the asteroid belt.
We can't physically get out to the asteroid belt yet as people. So meteorites allow us the chance to study the makeup of other worlds in our solar system.
There are sites that continue to be rich in meteorite finds. Brenham, Kansas has become famous for all sorts of digging.
This site here is the Brenham strewn field. Somewhere between 2,000 and 10,000 years ago, a giant meteor exploded coming in from the west-northwest, broke into a bunch of pieces and scattered pieces out in this farm ground out here.
Meteorites have definitely been found in this very field that we're in. It's exciting to be in a field. You know that they were here. Are there any left? That's what we're here to figure out.
To date, 4 tons of meteorites, pieces of our solar system, have been pulled from these fields, including Steve Arnold's find of a 1,430-pound, world record-sized Pallasite meteorite. These meteorites are composed of stone and iron and contain crystals of the mineral olivine. Pallasites are rare, valuable, and it takes work to find them.
In order to do that, we have a giant metal detector, which Steve designed and built. Maybe the largest metal detector in the world. It's certainly the largest we're aware of. It's called a pulse induction unit. That pulse induction coil sends an electromagnetic signal into the ground 600 times a second. It encounters metal buried in the ground. It creates what's called an eddy current on top of the object. That disturbance is then received by the coil, sent back up the communications wire to the box, and it produces a noise. And that noise tells us that there's metal in the ground. And Steve has a much more succinct method of describing how it works.
Yeah, I turn it on, and when it screams, it tells me there's metal, and that's where I dig.
Works every time.
The technology works, but the actual job of a meteorite hunter is all about patience. Like farmers working a field, Jeff and Steve must cover every foot of ground. Miss a spot, and they may miss the meteorite.
Okay. That's where we go pinpoint it, see what it is.
Digging is never easy, but there's an adrenaline rush that comes with the hunt. The possibility that they're standing on top of a meteorite worth tens of thousands of dollars makes the hunters dig a little less backbreaking. But no less disappointing when they find a so-called meteor rong, like this rusted wheel.
It's actually one of the cooler meteor rungs that we found.
No kidding.
but it's also worthless. Their meteorite hunt continues in a field 2 miles to the south.
Oh, well, meteorite hunting sounds like such an exciting and exotic lifestyle.
But this time, the excitement is actually warranted. They've hit something with a shape and metal content suggesting that it's a meteorite.
Looky there. Could be a fairly nice size, actually. Oh, got it. Yeah. Oh, look at that.
Congratulations.
Congratulations, buddy. Yeah.
This guy's been buried down there for, we don't know, 5, 10, 15,000 years. Just waiting for today. Be brought out into the light.
The meteorite's classic shape, its face flattened by the heat of entry into Earth's atmosphere, and its weight, around 40 pounds, could make it a premium find.
$20,000, $25,000, maybe?
When a meteorite arrives here, not only has it survived this incredible burning passage through our atmosphere, but it's a bit of the history of a long-vanished world that we'll never see, that we'll never get to. So we learn about the cosmos around us by studying meteorites.
Life. We search our solar system for extraterrestrial signs of it. We relentlessly investigate its origins here on Earth. But where did life really come from? Not just the first organisms, but the building blocks from which all life evolved. It turns out that cosmic collisions may be key to spreading the seeds of life throughout our solar system and the universe. Life on Earth formed roughly 3.5 to 3.8 billion years ago. Just as the chaos of our solar system's late heavy bombardment period began to die down, and conditions allowed for the formation of water. Amazingly, the asteroids and comets that crashed through the solar system during this period may have had a lot to say about when and where life formed. That's because the organic molecules that are the building blocks of life here on Earth can be found wafting through space in the cores of comets and on the surface of asteroids.
We are made up of much the same stuff that our environment is. In fact, even more so, we're made up of stuff that comes from heavy stars. As they explode and become supernova, and their material is spread all about through space. Some of it hits us in the form of comets, and then that becomes us. So in a way, we are star stuff, we are made out of comets.
Literally. For example, the iron in our bloodstreams was formed during the death of stars millions of years ago. In the latter stages of a star's life, after its fusion process has consumed its hydrogen and helium, it produces iron. That iron is distributed through space when the star dies and explodes. This distribution system scattered life's building blocks throughout our galaxy and beyond. So when we look up at the night sky, it's hard not to wonder if there's life out there. Surprisingly, collisions in our solar system can bring the search for extraterrestrial life right down to the surface of Earth. In 1984, in Antarctica, meteorite hunters found a strange rock that kicked off a storm of controversy about the possibility of life on Mars.
The meteorite itself was just a chunk of rock on the surface of Mars, happily minding its own business, when another large meteor hit the planet Mars and put enough impetus behind the rock to release it from the Martian